Hello students, welcome back to our channel Diksha Karnataka. So as you know, we have started a series where we are discussing on exactly how to prepare a topic, what all points you have to focus in this topic. So we have already done so many topics. So today we will be discussing the important topics under the chapter D and F block. Okay. So this is a moderate weightage topic. You can expect 2 to 3 questions from this topic. So let us see all the important topics and I'll tell you how to read and which trends you have to focus. Okay, so first let us have a quick glance on the topics. First is electronic configuration. You have to remember the electronic configuration from scandium to zinc. It is a must. Without this we cannot solve any question from here. Next is trend. So I'll be discussing all the important trends like your melting point, boiling point, atomic size. Then we have electrode potential, right? And then we have ionization enthalpy. So all the trends and what is the reason for this we will be discussing. Next we have KMnO4 and K2Cr2O7. So here I'll be telling you the preparation method and their oxidizing properties. And the last is F block elements. Here also some particular element electronic configurations you have to remember. And then what is lanthanide contraction and its consequences. Very important, right? Okay. So this after doing this, so we'll come to the first topic, that is the electronic configuration of D block elements. So I'll be marking certain elements you have to remember for all: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Here you have to be careful for chromium and copper. Okay, they have little different electronic configuration from all the elements. So focus on these two, and you should not only know the ground state electronic configuration, you should also remember the metal in 2+ oxidation state and metal in +3 oxidation state. Their electronic configurations should also be known. So I'll give you for one example. We'll take titanium. Titanium, if you see, the electronic configuration is 3d2 and 4s2, right? So if I take titanium 2+, you have to remove 2 electrons from the outermost shell. Okay, so the electronic configuration will become 3d2. So it's depend. I'm just giving one example. And suppose you have titanium 3+. Okay, then you will be removing 3 electrons. So 2 electrons from 4s and 1 electron from 3d. So I'll get 3d1. Now if I get titanium 4+, so we have to remove 4 electrons, 2 electrons from 4s and 2 electrons from 3d. So it will be becoming 3d0 and 4s0. Okay, so like this we can calculate the electronic configuration of any oxidation state. But for that, first of all, you should know the oxidation state in the ground state. So this table is a very important and a must remember, so that you can solve many questions and you can answer all the reasoning questions of this type. Now going to the next one. So I have already discussed what is there, what is D block elements. So D block elements are those where the last electron enters the penultimate shell of the D block elements. Okay, these are called D block elements. Now what is the general electronic configuration? N-1D, 1 to 10, Ns 0 to 2. Okay, so this is the general electronic configuration. Then we have the D block elements which have incomplete d orbitals are called as transition elements. This is very important. What is transition element? The condition for transition element is they should have incompletely filled d orbitals. Okay. Next we have the special category of zinc, cadmium and mercury. Okay, these elements have N-1 d orbitals fully filled in their ground state and also in their native state. Okay, ground state and common oxidation state. So as a result of which these 3 elements are not considered as transition elements. Okay, they are a part of 3D element, but they are not considered under transition elements. So certain reasoning questions you can get from here. You can get this question also: what is the general electronic configuration? Ns 1 to 2. Okay, so that is about electronic configuration. Okay, now we will go to trends. Okay, trends are very important. Certain trends you have to remember with reason, whether it increases or decreases. So first of all, coming to melting point and boiling point. You can see basically for all the transition elements, the melting point and boiling point are very high. Okay, what is the reason for that we'll discuss. But what is the trend along a period? Okay, if you see along a period, the melting point and boiling point first increases and then decreases. Okay, so these are 2 things you have to remember: first increase and then decrease. In general, the melting point and boiling points are very high. Okay, next, why the melting point and boiling point are high? That is due to metallic bonding. Okay, they have metallic bonding in them, and metallic bonding depends on number of unpaired electrons. Okay, so as we go along the period, the number of unpaired electrons keeps on increasing up to manganese, and then the number of unpaired electrons keep on decreasing. So that is why initially the melting point increases and then decreases. Now there is one more exception here. The melting point for manganese and technetium, Tc, okay, these are they fall regularly, that it decreases for manganese and technetium. So what is the reason for this? That is, they have a stable T5 electronic configuration. And two other things that you have to remember is tungsten, which is an element having highest melting point in the D element series, and we have mercury, okay, which exists in the liquid state. It is the only metal that exists in the liquid state. Okay, so these are some MCQ that you can expect. And other thing that you have to remember is first increase and then decrease. The reason is the number of unpaired electrons. Clear? Next trend will go. Yes, enthalpy of atomization. This also depends on number of unpaired electrons. Okay. So since they have more number of unpaired electrons, metallic bonding will be strong. So enthalpy of atomization will be high. Now again, there is a 3D elements. We have 4D elements and 5D elements. So the enthalpy of atomization of 4D and 5D will be greater than the 3D. Okay. So these points which are highlighted, you have to note it down and remember. Okay. Next is atomic radius, very important one. So first, what is the trend? If you see, generally along a period, the atomic radius decreases, right, because of effective nuclear charge. But in 3D series, what is the case? First it decreases, then it remains constant, and then towards the end it starts increasing. Now what is the reason for that? See, initially when it is decreasing, that is due to the actual cause, that is effective nuclear charge. When we go along a period, the number of protons are increasing, and the effective nuclear charge increases and the size decreases, right? Now what happens here? Why it remains constant? See, as we go along a period, the d orbitals are start filling, right? So we have, suppose this one is ns and this is n-1d, okay, and here we have the nucleus. So since this n-1d keeps on filling the electrons, that is an inter-electronic repulsion which tries to increase the size, and there is the nuclear charge which is trying to decrease the size. So there is a counter effect, and the net result is the size remains constant. Now when we go towards the end, where we have d10 electrons, right, here there are 10 electrons, inter-electronic repulsions are more powerful, and then the size increases towards the end, right? Is it clear? So there are 3 points. Initially when it decreases, that is because of effective nuclear charge. Then there is in the between, what happens? It remains constant due to two opposing force. One is the inter-electronic repulsion, another is the attractive force of the nucleus. Then towards the end, the inter-electronic repulsion dominates and the size increases, right? So you can see here from copper to zinc, the size is increasing, okay? Next is ionic radius. So ionic radius, you know, is inversely proportional to oxidation state. If oxidation state is high, then ionic radius will be less, and vice versa, okay? So here also you have to remember, just remember the trend. What is happening in the trend? So we have already discussed how many trends. See, first we have discussed about melting point and boiling point, then we have enthalpy of atomization, then we have atomic radius, ionic radius. Next is ionization enthalpy. This is also important one. As we know, along a period what happens? Size is decreasing, ionization enthalpy increases from left to right, okay? As we go along the period, ionization enthalpy keeps on increasing. Now here one more important thing is there. Zinc, cadmium and mercury have very high ionization enthalpy. See here, if you go along a period, okay, it is very clear that along a period the ionization enthalpy will be high. But what is strange is the zinc, this last elements, okay, their value is very high than expected value. And the reason for this is nothing but they have fully filled d orbitals. It is very stable, so it is very difficult to remove an electron from there, right? So that is why this is the statement. Now if you see 6d and 5d is more, ionization energy of 6d and 5d is more than 3d and 4d due to the actinoid and lanthanide contractions. So actinoid and lanthanide contractions starts from 5d and 6d. Due to this, there is more effective nuclear charge, and as a result of which ionization enthalpy further increases. Okay, next is your, so these are different trends. Now here these are some special properties that is shown by the transition elements. So you have to know what is the reason for that special property. So for example, interstitial compounds are formed with transition elements. With which type of elements they form? Hydrogen, carbon, boron and nitrogen. You can remember these 4 atoms. And for example, some example TiC is there, Mn4n is there, Fe3n is there. Okay, some 1 or 2 examples you can just remember. Okay, next is alloy formation. We know alloy is a mixture of metals in a proper ratio so that the properties can be improved. So what you have to remember is why transition metals can form alloy formation. That is because of they have similar radius. Okay, all the elements are having similar radius. It is easy to mix them, so we get this alloy. Now what are some examples? Brass is made up of copper and zinc, bronze is made up of copper and tin. So you can see copper and zinc are the transition metals. Copper is again a transition metal, right? Okay, now we'll go to another question, that is magnetic property. From here you can expect numericals. Okay, now magnetic properties are of 2 types, paramagnetic and diamagnetic. Okay, so if there is any unpaired electron, we call that substance as paramagnetic. And what is the meaning of that? It is attracted towards the magnetic field. Okay, attracted towards the magnetic field. Diamagnetic means it is repelled by the magnetic field, right? So here if you see, paramagnetic nature is directly proportional to number of unpaired electrons. So we have this formula, mu is equal to root over of n into n plus 2, where n is the number of unpaired electrons. So if more number of unpaired electrons means more magnetic moment. Okay, so from here you can expect numerical questions. You can also expect like 4 options will be given which is having highest magnetic moment, or arrange them in the increasing or decreasing order of magnetic moment. So such questions can be asked. So for that you should know the number of unpaired electrons, and that can be known if you know the correct electronic configuration. Okay, so very important topic. Next, this is complex formation. We have already seen in coordination chemistry that transition elements are involved in complex formation. So what is the reason why transition elements can only form complex? So we have 3 important ready because they have small atomic radius. Okay, next we have higher nuclear charge, and then is presence of vacant d orbitals. Okay, so you can remember these 3. So questions can be asked like, out of the following which is not a reason, or which is a reason that transition elements can form complex. So this is a very theoretical chapter, so you have to learn all the reasons basically. Okay, next is your catalytic activity. So again, why the transition elements can show catalytic activity? That is due to their ability to show variable oxidation states. Why they show variable oxidation states, that we will discuss. So examples of some reactions where transition elements are used as catalyst is V2O5, Fe. Okay, so you have to remember which almost every element doesn't react, but you can remember 2-3 examples. Now for formation of colored ions. Here, what is the reason for colored ions? Unpaired electrons in the transition elements show DD transitions, and hence they are colored. Okay, so here you have to remember that if there is unpaired electron, if we have unpaired electron, they can show DD transition, because of which they are colored. Okay, we have already seen in coordination chemistry also. So like here questions can be asked, which of the following is colorless, which of the following is colored. So the only one thing is it should have unpaired electron. Unpaired electron, it will undergo DD transition, it will show you color. So here one example, copper 2 plus. In copper sulfate, copper is in +2 state. Copper 2 plus is having electronic configuration of 3d9. It has 1 unpaired electron. So these 1 unpaired electron can undergo DD transition. Now if you see Zn2 plus, it is 3d10, no unpaired electron, so it cannot show you color. That is why it is white in color. Okay, so here also you can expect some application based question. Okay, so prepare this topic properly. Okay, so we have now next is oxidation states. So see, this point is very important. The element which can show large number of oxidation, this D block elements can show large number of oxidation states due to a reason called as there is n-1d and ns electrons participation. What is this? We have n-1d and ns electrons that participate in the bonding, right? So this is because of a comparable energy. Their energies are similar, they can participate in the bond formation. Now what happens, you have to remember one element manganese, it shows the highest number of oxidation states from +2 to +7. Okay, all the oxidation states are shown by manganese. Next we have oxidation state of the highest oxidation state shown by any element is +8, and that is which element? Your osmonium. Okay. Next we have copper 2 plus is more stable than copper plus and it undergoes disproportionation reaction. Okay, so I'll write down this reaction again here. 2Cu plus gets converted to Cu2 plus and Cu. Okay, so please ignore this reaction. So now you can see copper disproportionation reaction means the reaction in which the same element undergoes reduction and oxidation, right? So copper plus to copper 2 plus is oxidation and copper plus to copper is reduction. Okay. Next, this is important point. All the higher oxidation states of the transition elements can be stabilized by fluorine and oxygen. What is the reason for this? The fluorine and oxygen both are highly electronegative. But again, if we compare out of fluorine and oxygen, which can stabilize the higher oxidation states better, that is oxygen. Again, the reason for this is oxygen can form double bonds while fluorine can form only single bonds. I'll repeat this point once again. See, whenever there is higher oxidation state for any element, they generally form bonds with fluorine or oxygen at higher oxidation state. So this is because fluorine and oxygen are highly electronegative. Now if I compare out of fluorine and oxygen, which can be like more used than oxygen because it can form multiple bonds. Okay, so example you can see, when manganese is in +4 oxidation state, it forms bond with fluorine. Okay, but same manganese if you take in +7 oxidation state, it will prefer to bond with oxygen because it can have double bond here, right? So that is the important point here. Now we can go to electrode potential. This is again important one. So stability of a compound depends on the electrode potential. Okay, how much stable a compound is depends on its electrode potential. So if its reduction potential is high, it is not stable. If its reduction potential is less, it is stable. Like that we decide. But on what factors the electrode potential depends, that you have to learn. So there are three factors: enthalpy of atomization, ionization enthalpy, and hydration enthalpy. Okay, these three factors together decide the electrode potential, and electrode potential in return defines the stability of the ion. Now what is here? See, there is no regular trend from M2 plus to M. We cannot have any regular trend because there is no regular trend on these things. Okay, so because of irregularities in ionization enthalpy and the enthalpy of atomization. Okay, because of irregularities in these two, we do not have a regular trend for electrode potential. That is why we do not have a regular trend for stability also. So this is very important point, very important point. Please remember this one. Copper is the only metal with positive E0 value. You can remember the value also, 0.34 volt. Okay. Then what is the reason? Then what happens that it does not liberate hydrogen gas from acid. What is relation here? How to understand this concept? See here. Suppose any metal is there. Okay. And HCl is there. Okay. Generally we find salt plus H2 gas, right? So there is a possibility for the reduction of metal also, for the reduction of hydrogen also. Hydrogen reduction potential, if we have already discussed in electrochemistry, is considered to be 0. Now if there is two candidates to get reduced, metal also and hydrogen also, right? So if the reduction potential of metal is less than the reduction potential of hydrogen, then hydrogen will undergo reduction to produce H2 gas. And in the experiment, hydrogen gas is liberated. But if there is certain metal whose reduction potential is more than hydrogen, then that metal will be preferred for reduction and hydrogen gas will not be produced. So copper reduction potential, you can see it is 0.34 volt, which is greater than 0 volt. So if any reaction is there where copper and we have HCl, okay, copper 2 plus if you take, so copper 2 plus reduction will be preferred than the reduction of H plus. Okay, so that is why we cannot get hydrogen gas from acids in presence of copper. Okay, next is your chemical reactivity based on E0 values. So you have to remember reducing power is inversely proportional to E0 and oxidizing power is directly proportional to E0. So here questions are asked to arrange in the increasing or decreasing order. Values will be given in the table. You have to just check the values and arrange them. Okay, so next property is oxide formation. Here you have to remember a lot of oxides can be formed by transition elements. but oxidation state, if it is high, then acidic character will be more, and if oxidation state is less, then basic character it will be affected. Okay, so what is this? If higher oxidation state is there, okay, then it will be more acidic, and if we have lower oxidation state, then it will be basic. Okay, so here also questions are sometimes asked. Some compounds will be given, oxide compounds will be given. You have to arrange them in the increasing and decreasing order of acidity or basic nature. Here also you should remember some amphoteric oxides. Okay, some oxides are amphoteric in nature, like V2O5. Okay, so what is there? They can behave both as acidic and basic. Okay. Next, okay, so we will now go to some important compounds. So these are two compounds we have. One is potassium dichromate and another is potassium permanganate. So you have to learn there. These reactions are not asked, but the words you have to use. Like for example, chromite ore is taken to get converted to sodium chromate. Okay, then sodium chromate is treated with H plus to give you sodium dichromate. Sodium dichromate is treated with potassium to give you potassium dichromate. Okay, so these reactions and their oxidizing property, you have to remember their oxidizing properties. They are very good, very strong oxidizing agents. So those reactions and the preparation method you have to remember. Next, coming to potassium permanganate. So here we have two methods. One is manganese oxide converting to K2MnO4 and then manganese oxide getting converted to MnO2. Okay, so this reaction is not very important, but this one, the commercial method one. So this method is commercially used. So this one you have to remember. Okay, so here MnO2 is first converted to MnO4 2 minus, then MnO4 2 minus is converted to MnO4 minus. Okay, so MnO2 to MnO4 2 minus in presence of KNO3, and then MnO4 2 minus to MnO4 minus in electrolytic oxidation. Okay, so this is commercial method. Reactions questions can be asked from this method, please remember. Okay, and then you also have to do oxidizing properties of this one. Oxidizing properties of MnO4 minus. Okay, so actually both the oxidizing properties are very similar. Here we have acidic medium and basic medium, neutral medium. For K2Cr2O7 it is a common one. Okay, next we have, yes, so last topic, that is your F block elements. Here you have to remember all the elements, their atomic numbers. See, you have to remember the electronic configuration of certain elements which you cannot skip are cerium, okay, then you have europium and lutetium. Okay, these three elements electronic configuration you have to remember must, but I'll tell you to recommend like all the electronic configurations you have to do, but these three are mandatory. Okay, you cannot skip the electronic configuration of these three elements. Very, very important, because questions are asked on stability, existence, you will be getting from these elements. Okay, so ionization enthalpy, many questions you will get, you can solve it. Magnetic properties questions only if you know the electronic configuration. Okay, next is what is F block, we'll see. So when the electrons enter the F orbital of pre-penultimate shell, that is called as F block elements. What is the general electronic configuration? N-2 F1 to 14, N-1 D1 to 10 and NS2. Okay, now what are the common oxidation states? +2 and +4. So these are some general terms for F block elements which you should know. Now next, very, very important topic, that is lanthanide contraction. So what is lanthanide contraction? So let us see. The regular decrease in the atomic number in the atomic and ionic radii of lanthanides with the increase in atomic number from left to right is called as lanthanide contraction. So see, when you go along a period, okay, the size decreases because of increase in effective nuclear charge. But in case of lanthanides, there is one more factor which contributes to this, that is your 4f orbitals. These 4f orbitals have poor shielding. Why they have poor shielding? Because of their shape. Okay. So because of their diffuse shape, they are not very good shielders, they are very poor shielding, as a result of which the effective nuclear charge increases and the size decreases more steadily as expected. Okay, so that is why this is due to the poor shielding of 4f orbitals or 4f electrons. So lanthanide contraction definition you have to remember. and most important is the consequences. Okay, this is very, very important. Again, you will get many questions from lanthanide contraction. The reasons will be like the order, how to or basicity order, covalent nature. These all things you can solve if you have knowledge about lanthanide contraction. So first of all, what are the consequences? Separation of lanthanides is difficult. Because of the effective nuclear charge, the sizes are almost similar, so it is difficult to separate them. Then next one is basic strength of hydroxide decreases from left to right. So how will you explain what is basic strength? Basic strength is the ability to donate electrons, right? Now when the effective nuclear charge is increasing, it becomes difficult to donate electrons. So that is why we say the basic strength of the hydroxides decreases. Next we have covalent character of hydroxides increases. So there are two factors which decide the covalent character. First is the cation should be small, then the covalent character will increase. If the anion is large, then the covalent character will increase. Now as we go along a period, due to lanthanide contraction, the cation size keeps on decreasing and hence the covalent character increases. Okay. Next is very, very important. The size of the second and third series elements are almost same. Okay, so example is zirconium and hafnium. Okay, these examples you have to remember, they have similar size, and the reason for that is lanthanide contraction. So that's all in this DNF block. Very easy chapter, theoretical. So mainly focus on electronic configuration, the trends, and the preparation of KMnO4 and K2Cr2O7. Lot of questions will be covered from this topic. Okay. So if you have found this video helpful, please like, share and subscribe our channel for more updates.